Huffman codes and data compression. In the shortest path and minima spanning tree problems, we've seen how greedy algorithms can be used to commit to certain parts of solution, agencies in a graph in these cases, based entirely on relatively short-sighted considerations. We now consider a problem in which this style of committing is carried out in an even looser sense. A greedy rule is used essentially to shrink the size of the problem instance so that an equivalent small problem can then be solved by recursion. The greedy operation here is proved to be safe in the sense that solving the smaller instance still leads to an optimal solution for the original instance, but the global consequences of the initial greedy decision do not become fully apparent until the full recursion is complete. The problem itself is one of the basic questions in the area of data compression, an area that forms part of the foundations for digital communication. The problem: encoding symbols into bits. Since computers ultimately operate on sequences of bits, i.e. sequences consisting only of the symbols 0 and 1, one needs encoding schemes that take text return in richer alphabets, such as the alphabets underpinning human languages, and converts this text into long streams of bits. The simplest way to do this would be to use a fixed number of bits for each symbol in the alphabet, and then just concatenate the bit streams for each symbol to form the text. To take a basic example, suppose we wanted to encode the 26 letters of English, plus the space to separate words and 5 punctuation characters, comma, period, question mark, exclamation point, and apostrophe. This would give us 32 symbols in total to be encoded. Now you can form 2 to the b different sequences out of b bits. And so if we use 5 bits per symbol, then we can encode 2 to the 5 equals to 32 symbols, just enough for our purposes. So, for example, we could let the bit stream 00000 represent A, and the bit stream 00001 represent B, and so forth up to 11111, which could represent the apostrophe. Note that the mapping of bit streams to symbols is arbitrary. The point is simply that 5 bits per symbol is sufficient. In fact, encoding schemes like ASC2 work precisely this way, except that they use a larger number of bits per symbol so as to handle larger character sets, including capital letters, parentheses, and all those other special symbols you see on a typewriter or a computer keyboard. Let's think about our bare bones example with just 32 symbols. Is there anything more we could ask for from an encoding scheme? We couldn't ask to encode each symbol using just 4 bits, since 2 to the 4 is only 16, not enough for the number of symbols we have. Nevertheless, it's not clear that over large stretches of text, we really need to be spending an average of 5 bits per symbol. If we think about it, the letters in most human alphabets do not get used equally frequently. In English, for example, the letters E, T, A, O, I, and N gets used much more frequently than Q, J, X, and Z by more than an order of magnitude. So it's really a tremendous waste to translate them all into the same number of bits. Instead, we could use a small number of bits for the frequent letters and a larger number of bits for the less frequent ones, and hope to end up using fewer than 5 bits per letter when we average over a long stream of typical text. This issue of reducing the average number of bits per letter is a fundamental problem in the area of data compression. When large files need to be shipped across communication networks, or stored on hard disks. It's important to represent them as compactly as possible, subjected to the requirement that a subsequent reader of the file should be able to correctly reconstruct it. A huge amount of research is devoted to the design of compression algorithms that can take files as input and reduce their space through efficient encoding schemes. We now describe one of the fundamental ways of formulating this issue, building up to the question of how we might construct the optimal way to take advantage of the non-uniform frequencies of the letters. In one sense, such an optimal solution is a very appealing answer to the problem of compressing data. It squeezes all the available gains out of non-uniformities in the frequencies. At the end of the section, we will discuss how one can make further progress in compression, taking advantage of features other than non-uniform frequencies. Variable length encoding schemes before the internet, before the digital computer, before the radio and the telephone, there was the telegraph. Communicating by telegraph was a lot faster than the contemporary alternatives of hand delivering messages by railroad or on horseback, but telegraphs were only capable of transmitting pulses down a wire, and so if you wanted to send a message, you needed a way to encode the text of your message as a sequence of pulses. To deal with this issue, the pioneer of telegraphic communication, Samuel Morse developed Morse code, translating each letter into a sequence of dots, short pulses, and dashes, into a sequence of dots, short pulses. We can think of dots and dashes as zeros and ones. For our purposes, this is simply a mapping of symbols into bit streams, zeros and ones, as in ASC2. So this is simply a mapping of symbols into bit streams. One could communicate more efficiently by encoding frequent letters. Morse understood the point that one could communicate more efficiently by encoding frequent letters. He consulted the local printing presses to get frequency estimates for the letters in English. The local printing presses to get frequency estimates for the letters in English. T to 1, Morse code maps A to 0, a single dot. T to 1 maps more frequent letters to shorter bit streams. And in general maps more frequent letters to shorter bit streams. That the encoding of words becomes ambiguous. For example, just using what we know about the encoding of E, T, and A, we use that the streams 0101 could correspond to any of the sequences of letters ETA, AA, ETET, or AET. There are other possibilities as well involving other letters. To deal with this ambiguity, Morse code transmissions involve short pauses between letters, so the encoding of AA would actually be dot dash pause. This is a reasonable solution, using very short bit streams and then introducing pauses. But it means that we haven't actually encoded the letters using just 0 and 1. We've actually encoded it using a 3-letter alphabet of 0, 1, and a pause. Thus, if we really needed to encode everything using only the bits 0 and 1, there would need to be some further encoding in which the pause got mapped to bits. Prefix codes. The ambiguity problem in Morse code arises because there exist pairs of letters where the bit stream that encodes one letter is a prefix of the bit stream that encodes another. To eliminate this problem, and hence to obtain an encoding scheme that has a well-defined interpretation for every sequence of bits, it is enough to map letters to bit streams in such a way that no encoding is a prefix of any other. Concretely, we say that a prefix code for a set S of letters is a function, gamma, that maps each letter X in S to some sequence of zeros and ones in such a way that for distinct X and Y in S, the sequence gamma of X is not a prefix of the sequence gamma of Y. Now suppose we have a text consisting of a sequence of letters x1, x2, x3, and so on to xn. We can convert this to a sequence of bits by simply encoding each letter as a bit sequence using gamma and then concatenating all these bit sequences together, gamma of x1, gamma of x2, and so on until gamma of xn. If we then hand this message to a recipient who knows the function gamma, they will be able to reconstruct the text according to the following rule. Scan the bit sequence from left to right. As soon as you've seen enough bits to match the encoding of some letter, output this as the first letter of the text. This must be the correct first letter, since no shorter or longer prefix of the bit sequence could encode any other letter. Now delete the corresponding set of bits from the front of the message and iterate. In this way, the recipient can produce the correct set of letters without our having to resort to artificial devices like pulses to separate the letters. For example, suppose we are trying to encode the set of 5 letters S equals to the set A, B, C, D, E. The encoding gamma 1 specified by gamma 1 of A equals to 1, 1, gamma 1 of B equals to 0, 1, gamma 1 of C equals to 0, 0, 1, gamma 1 of D equals to 1, 0, gamma 1 of E equals to 0, 0, 0 is a prefix code since we can check that no encoding is a prefix of any other. Now, for example, the string CECAB would be encoded as 001, 000, 001, 1101. The recipient of this message, knowing gamma 1, would begin reading from left to right. Neither 0 nor 00 encodes a letter, but 001 does, so the recipient concludes that the first letter is C. This is a safe decision, since no longer sequence of bits beginning with 001 could encode a different letter. The recipient now iterates on the rest of the message. 000001101. Next, they will conclude that the second letter is E, encoded as 000. Optimal prefix codes. We've been doing all this because some letters are more frequent than others, and we want to take advantage of the fact that more frequent letters can have shorter encodings. To make this objective precise, we now introduce some notation to express the frequencies of letters. Suppose that for each letter x in S, there is a frequency fx, representing the fraction of letters in the text that are equal to x. In other words, assuming there are n letters total, n times fx of these letters are equal to x. We notice that the frequencies sum to 1. That is, the summations of fx summing for all x in S is equals to 1. Now, if we use a prefix code gamma to encode the given text, what is the total length of our encoding? This is simply the sum over all letters x in S of the number of times x occurs times the length of the bit stream gamma of x used to encode x. Using the size of gamma of x to denote the length of gamma of x, or say the absolute value, we can write this as encoding length equals to the summations of n times fx, the frequency, times the length of gamma of x, where we're summing for all x in S, which is equals to, if we take out n out of the summation, that will be n times the summations of fx times the length of gamma of x, summing for all x in S. Dropping the leading coefficient of n from the final expression gives us the summations of fx times the length of gamma of x, summing for all x in S, the average number of bits required per letter. We denote this quantity by ABL of gamma. To continue the earlier example, suppose we have a text with the letters S equals to A, B, C, D, E, such as that, and their frequencies are as follows. F A equals to 0.32, 32%, FB equals to 25%, FC equals to 20%, FD equals to 18%, FE equals to 5%. Then the average number of bits per letter using the prefix code gamma1 defined previously is dot 32 times 2 plus dot 25 times 2 plus dot 20 times 3 plus dot 18 times 2 plus dot 05 times 3. So the summation will be 2.25. It is interesting to compare this to the average number of bits per letter using a fixed length encoding. Note that a fixed length encoding is a prefix code. If all letters have encodings of the same length, then clearly no encoding can be a prefix of any other. With a set S of 5 letters, we would need 3 bits per letter for a fixed length encoding, since 2 bits could only encode 4 letters. Thus, using the code gamma1 reduces the bits per letter from 3 to 2.25, a savings of 25%. And in fact, gamma1 is not the best we can do in this example. Consider the prefix code gamma2 given by gamma2 of A equals to 1, 1, gamma2 of B equals to 1, 0, gamma2 of C equals to 0, 1, gamma2 of D equals to 0, 0, 1, gamma2 of E equals to 0, 0, 0. The average number of bits per letter using gamma2 is dot 32 times 2 plus dot 25 times 2 plus dot 20 times 2 plus dot 18 times 3 plus dot 05 times 3 equals to 2.23. So now it is natural to state the underlying question. Given an alphabet and a set of frequencies for the letters, we would like to produce a prefix code that is as efficient as possible, namely a prefix code that minimizes the average number of bits per letter. ABL of gamma equals to the summations of fx times the length of gamma of x, summing for all x in S. We will call such a prefix code optimal. Designing the algorithm. The search space for this problem is fairly complicated. It includes all possible ways of mapping letters to bit streams subject to the defining property of prefix codes. For alphabets consisting of an extremely small number of letters, it is feasible to search this space by brute force, but this rapidly becomes infeasible. We now describe a greedy method to construct an optimal prefix code very efficiently. As a first step, it is useful to develop a tree-based means of representing prefix codes that exposes their structure more clearly than simply the lists of function values we used in our previous examples. Representing prefix codes using binary trees. Suppose we take a rooted tree T in which each node that is not a leaf has at most 2 children. We call such a tree a binary tree. Further, suppose that the number of leaves is equal to the size of the alphabet S, and we label each leaf with a distinct letter in S. Such a labeled binary tree T naturally describes a prefix code as follows. For each letter X in S, we follow the path from the root to the leaf labeled X. Each time the path goes from a node to its left child, we write down a 0, and each time the path goes from a node to its right child, we write down a 1. We take the resulting stream of bits as the encoding of X. Now we observe 4.27. The encoding of S constructed from T is a prefix code. Proof: in order for the encoding of X to be a prefix of the encoding of Y, the path from the root to X would have to be a prefix of the path from the root to Y. But this is the same as saying that X would lie on the path from the root to Y, which isn't possible if X is a leaf. This relationship between binary trees and prefix codes works in the other direction as well. Given a prefix code gamma, we can build a binary tree recursively as follows. We start with a root. All letters X in S whose encoding begins with a 0 will be leaves in the left subtree of the root, and all letters Y in S whose encodings begin with a 1 will be leaves in the right subtree of the root. We now build these two subtrees recursively using this rule. For example, the labeled tree in figure 4.16a corresponds to the prefix code gamma 0 specified by gamma 0 of a equals to 1, gamma 0 of b equals to 0, 1, 1, gamma 0 of c equals to 0, 1, 0, gamma 0 of d equals to 0, 0, 1, gamma 0 of e equals to 0, 0, 0. To see this, note that the leaf labeled a is obtained by simply taking the right-hand edge out of the root, resulting in an encoding of 1. The leaf labeled e is obtained by taking 3 successive left-hand edges starting from the root. And analogous explanations apply for B, C, and D. By similar reasoning, one can see that the labeled tree in figure 4.16b corresponds to the prefix code gamma 1 defined earlier, and the labeled tree in figure 4.16c corresponds to the prefix code gamma 2 defined earlier. Note also that the binary trees for the two prefix codes gamma 1 and gamma 2 are identical in structure. Only the labeling of the leaves is different. The tree for gamma 0, on the other hand, has a different structure. Thus, the search for an optimal prefix code can be viewed as the search for a binary tree T together with a labeling of the leaves of T that minimizes the average number of the bits per letter. Moreover, this average quantity has a natural interpretation in the terms of the structure of T. The length of the encoding of a letter X in S is simply the length of the path from the root to the leaf labeled X. We will refer to the length of this path as the depth of the leaf, and we will denote the depth of a leaf V in T simply by depth T of V. As 2 bits of notational convenience, we will drop the subscript T when it is clear from context. And we will often use a letter X in S to also denote the leaf that is labeled by it. Thus, we are seeking the labeled tree that minimizes the weighted average of the depth of all leaves, where the average is weighted by the frequencies of the letters that label the leaves, the summations of fx times depth t of x, summing for all x in S. We will use ABL of t to denote this quantity. As a first step, in considering algorithms for this problem, let's note a simple fact about the optimal tree. For this fact, we need a definition. We say that a binary tree is full if each node that is not a leaf has 2 children. In other words, there are no nodes with exactly 1 child. Note that all 3 binary trees in figure 4.16 are full. 4.28, the binary tree corresponding to the optimal prefix code is full. Proof. This is easy to prove using exchange argument. Let T denote the binary tree corresponding to the optimal prefix code, and suppose it contains a node U with exactly 1 child V. Now convert T into a tree T prime by replacing node U with V. To be precise, we need to distinguish 2 cases. If U was the root of the tree, we simply deleted node U and use V as the root. If U is not the root, then let W be the parent of U in T. Now we delete node U and make V be the child of W in place of U. This change decreases the number of bits needed to encode any leaf in the subtree rooted at node U, and it does not affect other leaves. So the prefix code corresponding to T prime has a smaller average number of bits per letter than the prefix code for T, contradicting the optimality of T. A first attempt, the top-down approach. Intuitively, our goal is to produce a labeled binary tree in which the leaves are as close to the root as possible. This is what will give us a small average leaf depth. A natural way to do this would be to try building a tree from the top down by packing the leaves as tightly as possible. So suppose we try to split the alphabet S into two sets S1 and S2 such that the total frequency of the letters in each set is exactly one half. If such a perfect split is not possible, then we can try for a split that is as nearly balanced as possible. We then recursively construct the prefix codes for S1 and S2 independently and make these two subtrees of the roots. In terms of bit streams, this would mean sticking a 0 in front of the encodings we produce for S1 and sticking a 1 in front of the encodings we produce for S2. It is not entirely clear how we should concretely define this nearly balanced split of the alphabet, but there are ways to make this precise. The resulting encoding schemes are called Shannon-Fano codes, named after Claude Shannon and Robert Fano, two of the major early figures in the area of information theory, which deals with representing and encoding digital information. These types of prefix codes can be fairly good in practice, but for our present purposes, they represent a kind of dead end. No version of this top-down splitting strategy is guaranteed to always produce an optimal prefix code. Consider again our example with the five-letter alphabet. S equals to the set A, B, C, D, E and the frequencies. FA equals to 32%, FB equals to 25%, FC equals to 20%, FD equals to 18%, FE equals to 5%. There is a unique way to split the alphabet into two sets of equal frequency. The set AD and the set BCE. For the set AD, we can use a single bit to encode each. For the set BCE, we need to continue recursively, and again there is a unique way to split the set into two subsets of equal frequency. The resulting code corresponds to the code gamma 1 given by the labeled tree in figure 4.16b, and we've already seen that gamma 1 is not as efficient as the prefix code gamma 2 corresponds to the labeled tree in figure 4.16c. Shannon and Fano knew that their approach did not always yield the optimal prefix code, but they didn't see how to compute the optimal code without brute force search. The problem was solved a few years later by David Huffman, at the time a graduate student who learned about the question in a class taught by Fano. We now describe the ideas leading up to the greedy approach that Huffman discovered for producing optimal prefix codes. What if we knew the tree structure of the optimal prefix code? A technique that is often helpful in searching for an efficient algorithm is to assume, as a thought experiment, that one knows something partial about the optimal solution and then to see how one would make use of this partial knowledge in finding the complete solution. Later in chapter 6, we will see in fact that this technique is a main underpinning of the dynamic programming approach to designing algorithms. For the current problem, it is useful to ask, what if someone gave us the binary tree T star that corresponded to the optimal prefix code, but not the labeling of the leaves? To complete the solution, we would need to figure out which letter should label which leaf of T star, and then we'd have our code. How hard is this? In fact, this is quite easy. We begin by formulating the following basic fact. 4.29. Suppose that U and V are leaves of T star such that depth of U is less than depth of V. Further, suppose that in a labeling of T star corresponding to an optimal prefix code, leaf U is labeled with Y in S and leaf V is labeled with Z in S. Then Fy is greater than or equals to Fz. Proof. This has a quick proof using an exchange argument. If Fy is less than Fz, then consider the code obtained by exchanging the labels at the nodes u and v. In the expression for the average number of bits per letter, ABL of t star is equals to the summations of fx times depth of x, summing for x in S. The effect of this exchange is as follows. The multiplier on Fy increases from depth u to depth v, and the multiplier on Fz decreases by the same amount from depth v to depth u. Thus, the change to the overall sum is depth v minus depth u, then times Fy minus Fz. If Fy is less than Fz, this change is a negative number, contradicting the supposed optimality of the prefix code that we had before the exchange. We can see the idea behind 4.29 in figure 4.16b. A quick way to see that the code here is not optimal is to notice that it can be improved by exchanging the positions of the labels C and D. Having a lower frequency letter at a strictly smaller depth than some other higher frequency letter is precisely what 4.29 rules out for an optimal solution. Statement 4.29 gives us the following intuitively natural and optimal way to label the tree T star, and if someone should give it to us, refers to take all leaves of depth 1 if there are any and label them with the highest frequency letters in any order. We then take all leaves of depth 2 if there are any and label them with the next highest frequency letters in any order. We continue through the leaves in order of increasing depth, assigning letters in order of decreasing frequency. The point is that this can't lead to a suboptimal labeling of T star, since any supposedly better labeling would be susceptible to the exchange in 4.29. It is also crucial to note that among the labels we assign to a block of leaves, all at the same depth, it doesn't matter which label we assign to which leaf. Since the depths are all the same, the corresponding multipliers in the expression, the summations of fx times the length of gamma of x summing for all x in S are the same, and so the choice of assignment among leaves of the same depth doesn't affect the average number of bits per letter. But how is all this helping us? We don't have the structure of the optimal tree T star, and since there are exponentially many possible trees in the size of the alphabet, we aren't going to be able to perform a brute force search over all of them. In fact, our reasoning about T star becomes very useful if we think not about the very beginning of this labeling process with the leaves of minimum depth, but about the very end with the leaves of maximum depth, the ones that receive the letters with lowest frequency. Specifically, consider a leaf V in T star whose depth is as large as possible. Leaf V has a parent U, and by 4.28 T star is a full binary tree, so U has another child W. We refer to V and W as siblings since they have a common parent. Now we have 4.30. W is a leaf of T star. Proof: if W were not a leaf, there would be some leaf W prime in the subtree below it. But then W prime would have a depth greater than that of V, contradicting our assumption that V is a leaf of maximum depth in T star. So V and W are sibling leaves that are as deep as possible in T star. Thus, our level by level process of labeling T star, as justified by 4.29, will get to the level containing V and W last. The leaves at this level would get the lowest frequency letters. Since we have already argued that the order in which we assign these letters to the leaves within this level doesn't matter, there is an optimal labeling in which V and W get the two lowest frequency letters of all. We sum this up in the following claim. 4.31. There is an optimal prefix code with the corresponding tree T star in which the two lowest frequency letters are assigned to leaves that are siblings in T star. An algorithm to construct an optimal prefix code. Suppose that Y star and Z star are the two lowest frequency letters in S. We can break ties in the frequencies arbitrarily. Statement 4.31 is important because it tells us something about where Y star and Z star go in the optimal solution. It says that it is safe to lock them together in thinking about the solution because we know they end up as sibling leaves below a common parent. In effect, this common parent acts like a meta letter whose frequency is the sum of the frequencies of Y star and Z star. This directly suggests an algorithm. We replace Y star and Z star with this meta letter, obtaining an alphabet that is one letter smaller. We recursively find a prefix code for the smaller alphabet, and then open up the meta letter back into Y star and Z star to obtain a prefix code for S. This recursive strategy is depicted in figure 4.17. A concrete description of the algorithm is as follows. To construct a prefix code for an alphabet S with given frequencies, if S has two letters, then encode one letter using 0 and the other letter using 1. Else, let Y star and Z star be the two lowest frequency letters. Form a new alphabet S prime by deleting Y star and Z star and replacing them with a new letter omega of frequency Fy star plus Fz star. Recursively construct a prefix code gamma prime for S prime with tree T prime. Define a prefix code for S as follows. Start with T prime. Take the leaf labeled omega and add two children below it, labeled Y star and Z star. And if we refer to this as Huffman's algorithm, and the prefix code that it produces for a given alphabet is accordingly referred to as a Huffman code. In general, it is clear that this algorithm always terminates, since it simply invokes a recursive call on an alphabet that is one letter smaller. Moreover, using 4.31, it will not be difficult to prove that the algorithm in fact produces an optimal prefix code. Before doing this, however, we pause to note some further observations about the algorithm. First, let's consider the behavior of the algorithm on our sample instance with S equals to the set ABCDE and frequencies FA equals to 32%, FB equals to 25%, FC equals to 20%, FD equals to 18%, and FE equals to 5%. The algorithm would first merge D and E into a single letter. Let's denote it DE with a parenthesis of frequency 80% plus 5% equals to 23%. We now have an instance of the problem on the four letters S prime equals to A, B, C, and DE. The two lowest frequency letters in S prime are C and DE. So in the next step, we merge these into the single letter CDE of frequency 20% plus 23% equals to 43%. This gives us the three-letter alphabet A, B, and CDE. Next, we merge A and B, and this gives us a two-letter alphabet, at which point we invoke the base case of the recursion. If we would unfold the result back through the recursive calls, we get the tree pictured in figure 4.16c. It is interesting to note how the greedy rule underlying Huffman's algorithm the merging of the two lowest frequency letters fits into the structure of the algorithm as a whole. Essentially, at the time we merge these two letters, we don't know exactly how they will fit into the overall code. Rather, we simply commit to having them be children of the same parent, and this is enough to produce a new equivalent problem with one less letter. Moreover, the algorithm forms a natural contrast with the earlier approach that led to suboptimal Shannon-Fano codes. That approach was based on a top-down strategy that worried first and foremost about the top-level split in the binary tree, namely the two subtrees directly below the root. Huffman's algorithm, on the other hand, follows a bottom-up approach. It focuses on the leaves representing the two lowest frequency letters and then continues by recursion. Analyzing the algorithm, the optimality of the algorithm. We first prove the optimality of Huffman's algorithm, since the algorithm operates recursively, invoking itself on smaller and smaller alphabets. It is natural to try establishing optimality by induction on the size of the alphabet. Clearly, it is optimal for all two-letter alphabets, since it uses only one bit per letter. So suppose by induction that it is optimal for all alphabets of size k-1, and consider an input instance consisting of an alphabet s of size k. Let's quickly recap the behavior of the algorithm on this instance. The algorithm merges the two lowest frequency letters y star, z star in S into a single letter, omega, calls itself recursively on the smaller alphabet S prime, in which y star and z star are replaced by omega, and by induction produces an optimal prefix code for S prime, represented by a labeled binary tree T prime. It then extends this into a tree T for S by attaching leaves labeled y star and z star as children of the node in T prime labeled omega. There is a close relationship between ABL of T and ABL of T prime. Note that the former quantity is the average number of bits used to encode letters in S, while the later quantity is the average number of bits used to encode letters in S prime. 4.32 ABL of T prime is equals to ABL of T minus F omega. Proof: the depth of each letter x other than y star z star is the same in both T and T prime. Also, the depth of y star and z star in T are each one greater than the depth of omega in T prime. Using this, plus the fact that f omega equals to f y star plus f z star, we have ABL of T is equals to the summations of fx times the depth in T of x summing for all x in S. If we expand the definition, that will be fy star times depth T of y star plus fz star times depth T of z star plus the summations of fx times depth T of x summing for all x, which is not equals to y star and z star, which is equals to, if we combining the frequencies, that will be fy star plus fz star times 1 plus depth T prime of omega plus the summations of fx times depth T prime of x summing for all x, which is not equals to y star and z star, which is equals to, by the definition, that f omega is equals to fy star plus fz star. So we replace fy star plus fz star equals to f omega. So the form becomes f omega times 1 plus depth t prime of omega plus the summations of fx times depth t prime of x summing for all x which is not equals to y star and z star, which is equals to, if we expand the timing of f omega to 1 plus depth t prime of omega, that will be, if we separate that, distributed f omega to both terms, that will be f omega plus f omega times depth t prime of omega plus the rest term, the summations of fx times depth t prime of x summing for all x which is not equals to y star and z star, which is equals to, if we merge the last two terms, there will be f omega plus the summations of fx times depth t prime of x for all x in S prime, which is equals to f omega plus ABL of t prime. Using this, we now prove optimality as follows. The Huffman code for a given alphabet achieves the minimum average number of bits per letter of any prefix code. Proof. Suppose by way of contradiction that the tree T produced by our greedy algorithm is not optimal. This means that there is some labeled binary tree Z such that ABL of Z is less than ABL of T, and by 4.31 there is such a tree Z in which the leaves representing Y star and Z star are siblings. It is now easy to get a contradiction as follows. If we delete the leaves labeled Y star and Z star from Z and label their formal parent with omega, we get a tree Z prime that define a prefix code for S prime. In the same way that T is obtained from T prime, the tree Z is obtained from Z prime by adding leaves for Y star and Z star below W, omega. Thus, the identity in 4.32 applies to Z and Z prime as well. That is, ABL of Z prime equals to ABL of Z minus F omega. But we have assumed that ABL of Z is less than ABL of T. Subtracting F omega from both sides of this inequality, we get that ABL of Z prime is less than ABL of T prime, which contradicts the optimality of T prime as a prefix code for S. Implementation and running time. It is clear that Huffman's algorithm can be made to run in polynomial time in k, the number of letters in the alphabet. The recursive calls of the algorithm define a sequence of k-1 iterations over smaller and smaller alphabets, and each iteration except the last consists simply of identifying the two lowest frequency letters and merging them into a single letter that has a combined frequency. Even without being careful about the implementation, identifying the lowest frequency letters can be done in a single scan of the alphabet in time big O of k, and so summing this over the k-1 iterations gives big O of k squared time. But in fact, Huffman's algorithm is an ideal setting in which to use a priority queue. Recall that a priority queue maintains a set of k elements, each with a numerical key, and it allows for the insertion of new elements and the extraction of the element with the minima key. Thus, we can maintain the alphabet S in a priority queue using each letter's frequency as its key. In each iteration, we just extract the minimum twice. This gives us the two lowest frequency letters, and then we insert a new letter whose key is the sum of these two minimum frequencies. Our priority queue now contains a representation of the alphabet that we need for the next iteration. Using an implementation of priority queues via heaps, as in Chapter 2, we can make each insertion and extraction of the minimum run in time big O of log k. Hence, each iteration which performs just 3 of these operations takes time big O of log k. Summing over all k iterations, we get a total running time of big O of k log k. Extensions. The structure of optimal prefix codes which has been our focus here, stands as a fundamental result in the area of data compression. But it is important to understand that this optimality result does not by any means imply that we have found the best way to compress data under all circumstances. What more could we want beyond an optimal prefix code? First, consider an application in which we are transmitting black and white images. Each image is a 1000 by 1000 array of pixels, and each pixel takes one of the two values, black or white. Further, suppose that a typical image is almost entirely white. Roughly 1000 of the million pixels are black, and the rest are white. Now, if we wanted to compress such an image, the whole approach of prefix codes has very little to say. We have a text of length 1 million over the two-letter alphabet, the set black or white. As a result, the text is already encoded using one bit per letter. The lowest possible in our framework. It is clear, that such images should be highly compressible. Intuitively, one ought to be able to use a fraction of a bit for each white pixel, since they are so overwhelmingly frequent, at the cost of using multiple bits for each black pixel. In an extreme version, sending a list of XY coordinates for each black pixel would be an improvement over sending the image as a text with a million bits. The challenge here is to define an encoding scheme where the notion of using fractions of bits is well defined. There are results in the area of data compression, however, that do just this. Arithmetic coding as a range of other techniques have been developed to handle settings like this. A second drawback of prefix codes, as defined here, is that they cannot adapt to changes in the text. Again, let's consider a simple example. Suppose we are trying to encode the output of a program that produces a long sequence of letters from the set A, B, C, and D. Further, suppose that for the first half of this sequence, the letters A and B occur equally frequently, while C and D do not occur at all. But in the second half of this sequence, the letters C and D occur equally frequently, while A and B do not occur at all. In the framework developed in this section, we are trying to compress a text over the four-letter alphabet A, B, C, and D, and all letters are equally frequent. Thus, each would be encoded with 2 bits. But what's really happening in this example is that the frequency remains stable for half of the text, and then it changes radically. So one could get away with just 1 bit per letter plus a bit of extra overhead as follows. Begin with an encoding in which the bit 0 represents A and the bit 1 represents B. Halfway into a sequence, insert some kind of instruction that says, we are changing the encoding now. From now on, the bit 0 represents C and the bit 1 represents D. Use this new encoding for the rest of the sequence. The point is that investing a small amount of space to describe a new encoding can pay off many times over if it reduces the average number of bits per letter over a long run of text that follows. Such approaches, which change the encoding in midstream, are called adaptive compression schemes, and for many kinds of data, they lead to significant improvements over the static method we've considered here. These issues suggest some of the directions in which work on data compression has proceeded. In many of these cases, there is a trade-off between the power of the compression technique and its computational cost. In particular, many of the improvements to Huffman curves just described come with a corresponding increase in the computational effort needed both to produce the compressed version of the data and also to decompress it and restore the original text. Finding the right balance among these trade-offs is a topic of active research.